Hey folks, this is Todd Coburn of Cal Poly Pomona with the Aerospace Structures series. This morning I'd like to cover some basic information that's needed by every engineering student and professional. That involves what could be termed engineering graphics or drafting or engineering visualization and sketching. These are key skills that every single engineer needs, and we ought to be honing those skills all the way from the time we start on our engineering journey as an undergraduate student on into graduate school and out into the field. Today I'm going to keep it really simple and cover some of the basic principles that need to be understood by every engineer. Study this carefully, practice all the time, and be watching for future updates where I add additional content. Enjoy. So first we're going to start off with understanding projections, visualization, and sketching or views. Okay, so let's take a look at this idea first. Starting off with projection, what we're going to be doing is one key skill of engineering is being able to visualize how something looks on flat paper. We see an object, we draw it on flat paper. We imagine an object, we draw it on flat paper, and then we learn to transform those views, those flat views, into three-dimensional structure. So first being able to draw what you see, and then being able to transfer from a three-view drawing to a isometric view drawing. We're going to cover all these principles. The first idea is the idea of projection. The way drafting works is we're going to be drawing what we see. As you see in this upper left picture, this guy is looking at an object. There's an object sitting out there, and it's as if we put a pane of glass between the eye and the object, and we're sketching what that view looks like. Now that's going to be scaled based on the proximity of the glass relative to the part, but we don't need to worry about that just yet. Okay, so this idea of a projection plane that we're looking through like a piece of glass that we're sketching the item on. Okay, second idea is how we're going to represent this. So there's a couple trains of thought on this, but let's just take a look at this rightmost figure where we see a standard coordinate system. We see the first quadrant is the one nearest to us, the second quadrant off to the left, then the third down below, and the fourth. There are two major methods used for representing structures when they're being drawn. One is called first angle projection, and the other is called third angle projection or quadrant projection. Imagine we have a part and it's sitting in this first quadrant. If that were the case, then one way to represent that object would be to draw how it looks or the shadow of it on the planes behind it. This is called first angle projection, as if we have that object sitting in the first quadrant and we're seeing how it shadows on to the planes behind it. That is not consistent with our projection discussion a moment ago. Another idea is to place that object down in the third quadrant. In that case, you'll see that we're going to be looking through that coordinate system, through those planes of the coordinate system. We're going to look through this plane to see the part, look through this plane to see the part, look through this plane to see the part. That is consistent with the projection idea that we just presented. Now, the UK used to use first angle projection a lot, but the US uses third angle projection. As I understand it, since about World War II, I believe most of the UK is probably doing the same thing with third angle projection. So we're going to be using third angle projection. Okay? So let's see how this works. Now, if we were to take that first quadrant and place our object there in that first quadrant, then this is how those views would be shown. We would be looking at the part and drawing how it looks on the plane behind it, as if the shadow lies on the part. How it looks looking through the part onto the plane behind it, looking through the part onto the plane behind it. This is first angle projection. And once again, we're not going to use that. We don't use that in the United States. Now, if we took the part from the third quadrant, that other down below quadrant, the third quadrant, this is how that part looks, this lower left picture. And now we're looking through the projection plane at the part, through the projection plane at the part, through the projection plane at the part. That is how third angle projection works. In fact, we can take a look at this part. You can see that also, if the part's here, there's a plane back here that we can look through, and a plane back here that we can look through, and a plane down below that we can look through. And what we can do to see all of the views of the part is fold out this box. So taking a look, if we grab that front view and we place it right here on that front view, you can see this kind of central, this other picture, and then we fold out the other pages above and below. That's how third angle projection works and how we open up the views of the part. We're going to look at that a little further in a moment. And each of the sketches, those flat sketches, will be drawings of how that part looks through that plane. Any parts that we can see, like fold lines and things, will be solid, and any that we can't see because they're actually there but they're maybe beyond the part, the parts are solid, we can't see them, those will be shown as dashed lines. Okay? Now, so what we see over to the upper left is first angle projection, down below is third angle projection. We're using third angle projection in the United States. The way this shows on drawings is they'll have a little sketch like this symbol shown up at the upper right. You'll see that first one, that symbol with a part and its other view represents first angle projection, and the lower one represents third. As you can see, as if we're taking this one view and now we're folding out the other view. Or you can imagine putting your hand on an ink stamp, and here's the part we're grabbing the front of that cone. We take this ink stamp on our hand. We just got our hand all dirty with it. We smack the side of the part and then smack it down on the page. We fold it out and smack it down on the page. That's how that works. If we did a top view, we'd smack it on the part and then we'd rotate it out and bang onto the page. Smack it on the part, rotate it out, bang it on the page. Smack it on the part, rotate it out, bang it on the page. If we wanted to do the back, we'd smack it, and then we'd have to rotate, and it'd be all the way up here above the other view. Or, in the case of this drawing, we'd smack it here, and then we're rotating and rotating to get that last back view. We're going to see more of this in a moment. You can come back to this and study this at your leisure to make sure you understand it. So once again, here's a part sitting in our projection box, and all views are going to be as if this glass box is around it, and now we're going to look through each of the glass panes and draw what's on that. We're going to have the side view, or what's called the right view. We're going to have the front view, how that looks through this plane, the left view, how that looks through this plane, and so on. You'll notice on the right view, we can see the lower edge of the part, the middle edge where the part creases, that's shown as a solid, and the top of the part, and the two sides. If you go around to the left side, you'll notice you can see the top, the bottom, and the two sides, but you can't see. On the other side is this other crease line. You can't see it directly, so we show that as a hidden line. A hidden line, which means a dashed line. Looking from the top, we can see where that part has this joggle. That's a solid, but looking from the bottom, it's on the other side of the part. You can't see it directly, so it's shown as a dashed line, which we call a hidden line. So solid lines we're going to use hidden lines to represent, or dashed lines to represent hidden things, edges that we can't see directly. And then we'll later use, and we're not going to cover that in this video, center lines, which is a long, short, long, long, short, long, to represent center lines of holes and things. Now, so if we want to show all the views of the part, we choose a view that we want to be the front view. Usually what we'll do is, even though it's kind of shown as a certain view here, usually an engineer will select the view that gives the most information about the part, and they'll call that the front view, and then all the other views are represented relative to that. So if this is the front view here. Then this over here is the right view. This is the left view. This is the back view. This is the top. This is the bottom. In order to see how all of the views lay out, we grab that front face and we imagine unfolding the box, unfolding the box, unfolding the box, unfolding the box. And then over here, to get this back one, we've got to unfold, and then it comes out and folds out with this other view. It shows up all the way over there. See how that works? That's how it works. I used to, actually, you can cut out a piece of paper in this shape and fold it out. I should make a little video on that to show you how to do that. It's a really good way to visualize. Okay? So that's how that works. Let's look at it further. So here are some common parts. We can see the same view over here to the left. We see the front view, and you'll see there's the part on the right, and then the projection of that plane onto that glass panel. Down below, we see the top view is as if you're looking down, and we see how that looks from the top. You can see how the right side view is coming in from over here. And that's a little confusing, but the left side view is shown in this panel down below over here, where basically it's like we're projecting that out, projecting the bottom view and projecting the back view. Once again, we're going to take that front view, grab that first, and then fold it out. So you look at this upper right, we'll see how we fold out, fold this part out twice, fold the top, and fold the bottom. That's how it works, okay? And when we're laying out these views, we can use what's called the miter line, which is this 45 degrees going between the true views. We're going to look at that again in more detail momentarily. You starting to get the picture? Stand by. Okay, so how many views do you show? So you got all these views, but a lot of them are redundant and unnecessary. For example, if we had this part shown here, this isometric view that's shown here, then we can see the 6 views, that's in figure A, the 6 views are shown in figure B. You can see the front view, that gives the most information, the right, left, rear, top, and bottom views. But you'll notice that the front view and the back view are pretty much identical information, so we don't need the back view. You can see that the right view and the left view are pretty much the same information, so you don't need the left view. Now, sometimes we'll make a decision. We'll look at these two views, which one to eliminate, and we will eliminate the one that has the least information. So if in one view it's all solid lines because you can see them directly, that's a better view to draw than the one that has a bunch of hidden lines. So we'll often try and orient our part to select those, but sometimes the front view choice will define how we roll that out, just a right and a top view. It's more common to show the right and top view with the front view rather than the rear and top or rear and bottom. So often we break that rule, if you want to call it that, in order to show more of a standard set of views. So when we get done, we find out we really only need 3 views to represent this part. And we're going to find for most engineering parts, we only need 3 views. Now, some parts, actually 2 views is sufficient, like a cylinder that we saw before, or a sphere. But most engineering parts, you'll need a 3-view drawing to show it completely, and you don't need any more views than that. Every now and then we'll have a more complicated part, and then we'll pull off additional views, often true length views called our auxiliary views. We're not going to cover that yet, not in this video. Maybe in the future I'll add that content. You still with me? Okay. So then we're ready to start taking a look at, okay, well, let's start drawing some 3-view drawings. So here's how it basically works. Once again, we said typically we're going to use 3-view drawings unless we only need a 2-view drawing. And basically we're going to need to lay them out in our drawing space. Now, as an engineer, even when you're not doing drafting or defining of a part with drawings, you are going to find there's a lot of times when you need to be able to sketch your part or the views of a part quickly and accurately. In that case, you don't have to spend a lot of time laying it out. But whenever you're doing a real engineering drawing, you're going to need to figure out how this looks on the page. You're going to want to pay attention to your margins and how much space is between the part, so you represent the part in a clear and understandable manner. Remember, engineering is about not just coming up with ideas, but being able to put them on paper so these ideas can be built with a repetitive and verifiable manner. Okay, so often we're going to use 3-view drawings. Sometimes we'll only need a 2-view drawing if those 2 views are sufficient. If doing a 3rd view would be kind of redundant, then we only need a 2-view drawing. When we draw these views, once again, this is kind of how it's going to work. If you take a look at this lower left panel of the left picture, we see, well, actually, let's start with the top view. You'll see that we kind of have our total drawing space laid out here because you want that to set within your drawing space. We're usually going to start by drawing our front view of the part. And then what we're going to do is extend leader lines through every feature so that we can get where those belong in the other view. And we'll extend horizontal leader lines to get our right view. We're going to find that if we follow the basic procedure, then we can use what's called a miter line to transfer dimensions from one view to another view. For example, in this particular case, if we drew our front view here, then right here, if we draw our front view, we then can use miter. We can draw leader lines through each feature. That's a crappy line. And that allows us to lay out our other views. So now we can say, okay, let's decide to have the front face here. And now we can measure the depth of the part, and we have the top view. Now, if you now extend the near face of this view and the near face of this view until they touch, and then draw a 45 degrees, that's called the miter line from that point, then actually you can transfer the dimensions with leader lines from this view down onto this view. See how wherever this projected line hits this line, it transfers down. Now, if this space here is the same as this space here, then this 45 degree will come right through this point. But if these two spaces are different, then they won't come from this point here, but wherever the front face and the front face, or the near face and the near face meet, that's where you draw your 45 degree angle from there. Do you see how that works? And then, now what we normally do, if you're learning drafting by hand, you're going to learn about line quality and how you can have a nice bold line for the edges of your part. And these leader lines are going to be really faint with a super hard and fine lead, so they hardly show when you go and photocopy this, so you don't have to do a lot of erasing. When you're all done, you're going to have 3 views shown like this that are differentiable. So once again, we first draw the front view, and then we draw either the top view or the side view, either one. And then once we finish that view, we extend the view through the miter line, having extended these two closer near faces, and then we can transfer our dimensions to the other side and across like this. That's how it's done. Here's another view. This is showing the 45 degrees in the miter line, and this is how our final views work. Got that? Okay. If you want to learn how to draw an engineering drawing, now this doesn't have anything about title blocks. There's a whole art to drawing the correct title blocks as well. I'm not going to cover that, at least not yet. But to lay out your drawing, you'll notice if you just start drawing your front view and then start worrying about your other views, it's not going to probably align with your paper very much. This is why you want to do a little planning. Figure out what are the overall dimensions of the front view. What are the overall dimensions of the top view and the side view? What is the total dimension going horizontally of the front view plus the right-hand view relative to the size of your paper? You can then do some scaling to figure out a nice comfortable margin for the edges and a comfortable margin for the middle. And you can do the same thing with the top. The margins for the top and bottom views versus the middle. And you're going to line, once again, you're going to line the top view directly above your front view and the right view directly to the right of that view. And the front faces, wherever they meet, you're going to draw your miter line from that point. I like to keep this dimension C and D the same. Then your miter line can extend all the way from the upper right corner of your front view. However, that's not required. The D and C can be different as long as you draw your miter line from that intersection point of the two near faces. Here is a little procedure I laid out for you guys to do that in a repetitive fashion. So let's take a look at our views and make sure we understand it. We've got basically everything we need to know about visualization. Now we just need to practice. We need to be able to go from a 3-view drawing to an isometric, or from an isometric to a 3-view drawing. And the first step is being able to understand those views. Let's go back to our part. If we have this part here, we see, for example, this point 1 shows up in our 3 views. If you look down on the thing, it's this little point right here. If you look at the front view, you see that point is right here. And if you look from the right view, you see that that point is over here. Similarly, if we take point 2, which is that lower, that corner way back behind the part, you see from the top view, we see looking down, it looks like it's right on this corner here. Looking from the front, it looks like it's right down here. And looking from the right view, it looks like it's on the back down over here. Same thing you can see, trace out that point 3. This is really good practice. You can do the same thing for an isometric. If we have an isometric like is shown here, you'll see this point 1 is shown. You'll see this point 1 is shown here, and looking from the top it's here, and looking from the right it's right here. I'll leave it to an exercise you to trace out all these points and make sure you can see how these points, like point 11, shows up here, and in this view it shows, actually it's not shown, but actually in the front view it would be right there in line with 9 and 10 and 11 and 12. That point is all of those points. Do you see how that works? Here's another one we can practice on. Let's take point 14. You'll see on the front view how you're looking right down this edge, 114. From the right view, you're looking right down this edge, 1314. And from the top, you're looking right down this edge, 14 and 9. See how that works? Let's practice this a minute. Now, in order to do this now, when you take drafting, if you took drafting a decade or two ago, you would have been doing all this on paper using the right leads in your pencil and everything else. Nowadays, a lot of this is done with CAD. And there's a lot of benefits to doing it with SolidWorks, AutoCAD, or other CAD tools, CATIA. However, I think we lose something when we go straight to CAD. We should first be able to do this visualization and sketching on paper. And even though it's of a lot of use to learn how to do this precisely and neatly so that your drawings are quality engineering drawings that can be used, it's actually, you can get a lot of practice by just sketching and learning to sketch in a systematic way so your drawings are understandable. And to do this, you can do this quite quickly without even using your scale. Okay, I'll give you a method to do this even faster in a little bit. Let's take a look. Let's say we have an isometric like this and we want to draw it. If I looked at this, I'd say, okay, probably the view that gives the most information is looking from right here. I'm going to call that the front view. That means this over here is going to be the right view, and this up here is going to be the top view. So I'm going to lay out my view front, top, right. Okay, let's see how that works. Once again, what can really help is if you just have quad paper. If we had quad paper, then those quads can help us. You can see we've got, first we draw our front view, we draw our leader lines going up for each feature, and then transfer our features from the one view to the other. So we see here that we see if we draw this view to scale, then we extend our leader line up. You see this defines this edge here. This line here only comes in for this first. We have this little dimension here, right? And that's how long this is. And we have the width of the part. That's this dimension here. We have this dimension here, which translates to here and specifies this piece. We can measure from here to here, and that tells us where this plane is, which we draw here, and we measure from here to here to get this line here. We can measure the height of the thing, and that tells us how long this is, and we draw this line, taking this dimension along here and this dimension along here. We see that this then goes down right along here. Actually, both this line and this line are represented by this. This line is represented by this and this, what we can't see back there. Now we can bring this across here by measuring from, actually we want to extend this to here and then measure to the bottom. That tells us where this line goes. Now we extend our leader lines, and that gives us these dimensions. We can draw the back of this part, the front of this part, and we see if we measure this dimension here, we see where this hidden line belongs. This cannot be seen from this edge. You have to look, see if you're looking this way, you have to look through this part to see that projection there. That's why this line is shown as a hidden line. And this is the same dimension as this, and now we have that. And then this one also can't be seen, so this is also a hidden line. Now, if we extend up the front face of this drawing and the near face of this drawing, then we put our miter line here, and then we can just bring these dimensions, and that will tell us where these lines go. This comes up to here and here, and so that tells us where these lines go. And this goes to there, and then this one here tells us where this goes. And this one here tells us where this goes. This one here tells us where this goes. This line here tells us where this goes. This line here tells us where this goes. This goes. Bang! That's how it works. Got it? Now if we have a part like this, once again looks like this is the front view. That makes this the right and this the top. First we sketch our front view and then we sketch our top view. In this particular case we can look and say, this third view is kind of redundant. I probably would have drawn it. If we were going to draw it, we would extend our line like this. We'd extend our line like this. We would extend this line like this. We would extend this near line like this. We choose where we want this to go. Let's say we're going to put it here. That defines where the miter line goes. And then we can bring this over, and that tells us where the back is. This over, and that tells us where this other surface is. And looks like that's about it. So when we're all done, we see, looking at this part, we have this part here, and we have this line going up to here, and then we see this face here, and this comes down here, just like this. Let's go and erase the pieces we don't need. Let's see, this is not here. This part right there, let's redraw that. Oh, we got that fixed. That looks like it. Now we have represented that part. Does that make sense? That's how it works. Now let's say instead we have a two-view drawing. In this case, we would sketch it out like this. Here's how that works. So we would come in here, we'd say, okay, we're going to have an isometric drawing, and therefore, let me see if I can do it down here on my other screen. Let's see if we can do it here without messing everything up. So what we're going to do is we've got a part, we're going to do it like this. Here and here and here. I take this dimension and say, okay, it's about like this. I take this total dimension and say it's about like this. And I've got this dimension, that tells me how tall it is. And I'm going to basically box this part in with the overall dimensions of the part. Then I'm going to look and say, okay, this is about this high up, so it looks like it's on the back side, so I'll measure that height to here. I'll take this measurement here and draw it there, so that tells me parallel to this, that tells me where that point is. And then this goes up once again. If we look on the back face, this same width is like this. So wherever that would have hit here is where it hits back here. This is how it's coming. Now this piece here is this thick, so we can just take that measurement along here, and that's the same measurement as down here. That gives us this part of the part, and then we can see that this goes parallel to this line until it strikes here. So what we see is that the part does this. Now we can measure this dimension here along this line, and that tells us where that part is. So now we say, great, I think we just about got it. So we can take parallel to here, parallel to here, parallel to here, and then this line goes from here to that point, this line goes from here to this point. Then all we got to do is, let's go up one. If I can, I didn't mean to do that. So then what we do is just erase these pieces that we don't need. Our basic final part looks like this. Now I've drawn these all with this crappy line that you can't tell the difference, but that's now how this part looks. If we look at this face here, you see that that's this face here. Let's call this 1. And this face over here, 2. This face along here, that's 3. Up here on the top, we'll call that 4. That's this area here. This slanted area we'll call 5. That's along here. This little frontal area here and here, we'll call that 6. See how that works? And then back here, this is the back of our part along there. That's how we go from, and you'll see how quick that is, and you can do it even quicker as you get a little bit of experience. So you can practice going from a 2-view or a 3-view flat drawing to an isometric. You can go from an isometric to a multi-view drawing. Here's another example. Once again, we have this part, and we can lay it out the same way. It looks like something like this. Now, in order to make this, you'll notice that I have lines on this paper. Now, you can do this all with your scale, just measuring all these dimensions. But if you get some isometric paper, this over here on the left is just quad or quint paper. Quad for 4 squares per inch, quint for 5 squares per inch. I prefer the quint because now you have every square is 2/10 of an inch. It's a nice, easy to transfer dimensions in a decimal fashion. It's really easy to write on this paper. Let's practice a part on this real quick. Let's say we have a part that looks like this. Let's say we want to draw a part that if we just box that puppy in, let's say it looks like this. Let's say that's our part. Here, 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 and here, okay? Forget these extra lines that I drew in laying these out. So first we'll take the overall dimensions. We're going to need this length, and we're going to need the height. So we'll start off with this length and the height, okay? And then from that, we can say, okay, we're going to bring dimensions along there. Then we take this dimension here, and we'll put it right here. Connect these 2 lines and square in our piece. If we bring this up, we then see, okay, let's say we're going to start this edge right here. So we draw this line along here, and then we take this dimension that tells us how deep it goes, and then we extend this line, and let's just say we're going to start the near face right here. So if the near face is right here, once again we're going to take this dimension and lay that out here, and then this dimension comes across to here, and this dimension comes to here, just like this. Bang. Then we go up to our miter line, and these dimensions will all agree here. When we're all done, we're going to have three faces. You'll notice this front face, right, is this face here. This face here is this face here. This canted face is actually this and this. Now you can't measure on those because it's oblique, it's not flat. You can only measure on planes that are parallel, on surfaces that are parallel to the plane that we're viewing. Anyway, that's how it works. Now if we have this 3 view and we want to draw it over here, you can do the same thing. Once again, you'd find a starting point. You'd take this dimension here and you'd lay it out here, right? You take this dimension here and you'd lay it out here, and then you would take the height of the thing, you'd lay it out here, and then you take this height and you lay it out here, and then you follow this isometric line, and then you connect these 2 points, and you take this same width is the same width here, right, whatever that width is, and it looks like it's let's see, so what do we got? 1, 2, 3, 4, 5, 6, 7, 8-ish. 1, 2, 3, 4, 5, 6, 7, 8-ish. So that's that dimension. This comes up to here. And now we have that 1, 3, and 2. See how easy that is? This is called quad paper or quint. Remember, this is 4 squares per inch. This is 5 squares per inch. This is isometric paper, which is a nice, easy way to sketch a 3 view. Getting this kind of paper and practicing is really healthy, and after a little bit of practice, you'll be able to do this without the fancy paper and have your drawings be legible. If you have a little artistic talent, obviously that makes it even better, but even without artistic talent, if you want to be in engineering, you need to be able to document how your parts are made and understand how other people have made their parts. Okay, so that's what we need to understand. I'm going to encourage you to study this material. Enjoy.